work in that? Yeah, okay. This is an identity. What property is this? Distributive property. Distributive property works for any value of x. It will always be true. All right, so what about this? 2x plus 3 equals 7. Identity or not an identity? Ah, resounding not an identity. What value of x does that work for? Does it work for any other value of x? No. So the identities are the ones that work for all values of x. So we're going to write down that definition. See if you can fill in the other 5 reciprocal identities if you know this one. All right, so 90% of you seem to be right on point. For secant, we have 1 over cosine of x. For cotangent, we have 1 over tangent of x. Sine, maybe less familiar, but still works. Sine is 1 over cosecant of x. Cosine is 1 over secant of x. And tangent. All right, so we've seen these before. No news flash here. Just remember what they're called, reciprocal identities. The next set of identities, quotient identities. And I've limited this list to just 2. These you also know already, even though you may not know what they were called up until now. Quotient identity. Anybody think they have an idea of what I'm talking about there, Matt? Good. Sine of x over cosine of x. I know there's a temptation here to be lazy and not write the letter x. Don't do that, please. We want to be precise. Matt was very precise with how he said that one. Let's all be precise. For cotangent of x, what am I talking about there? Matt got the last one. This one's very similar. Cosine of x over sine of x. So these are our quotient identities. No news to us. We knew this already. All right. Then Vaishu mentioned another set of identities that we talked about briefly, and you may have seen in Math 3 if you took that before you came to pre-calculus. The Pythagorean identities. When you hear Pythagorean, what shape do you think of? What type of I said it, never mind. Right triangles. All right, this only works with right triangles. We looked at a bunch of different right triangles. In fact, we cut out right triangles when we were working with the unit circle. So, we've seen these before. For all the triangles that we drew in the unit circle, what was the length of the hypotenuse? 1, okay? And the horizontal distance from the origin was always the same as which trig function? This horizontal distance was the same as which trig function? Cosine. So cosine of x for the horizontal distance, and then the vertical distance was always the same as which trig function? I heard 2 things. The sine. So the sine of x is this one. All right? So we've got a right triangle. That's what Pythagoras used. We've got all 3 sides in the right triangle, so now we just have to write the identity, which you guys have probably already written at this point. Pythagorean theorem says a squared plus b squared equals c squared. What does that mean in this triangle? All right, so it's like we're singing row, row, row your boat in a round there. We were all saying it at different steps. Cosine of x squared, which can also be written like this. Cosine squared of x with the exponent between the cosine and the x is the same thing as cosine of x squared. Normally we will see it written the first way, not the second way, so that's what I'm going to do in my notes. Cosine squared of x plus the sine squared of x is equal to 1 squared, which is just 1. All right. This is one of 3 Pythagorean identities. The other 2 come from this one. And what we do to get the other 2 is we divide by a carefully chosen trig identity. The first one we're going to divide by, and you guys can simplify this as soon as you are ready. We're going to divide every term in the original Pythagorean identity that we got from the unit circle by the cosine squared of x. So now we need to simplify all these. You can simplify each of these using the identities on the previous slides or in your notes right above this. Don't forget that when you divide something by itself, you always get 1. All right. So the cosine squared of x divided by the cosine squared of x, you should have gotten 1 for that. What's the sine squared of x divided by the cosine squared of x? Tangent squared of x. And 1 over the cosine squared of x is secant squared of x. So that's our second of 3 Pythagorean identities. We got this one by dividing everything in the original by cosine squared. How do you think we're going to get the third one? Divide everything by sine squared of x. So go through, write that down if you want or need, and then see what you get when you simplify. Colton?
Why do we call them identities instead of formulas? What do you think, Ms. Chen?
Well, that's the vocabulary. That's a good question. That's the vocabulary word we've chosen. But Saurav's right. We don't plug things into this. We just use them to simplify. So kind of like distributive property. We're not really plugging things in. We're using it to simplify the equation or the expression. But that's a good question. I haven't looked into the history on that. So, all right. What do you get when you simplify this one? Cosine squared of x divided by sine squared of x is... All right. Now I'm not getting 1 first here. Cosine squared of x divided by sine squared of x is cotangent squared of x. And then we have the 1 followed by cosecant. Okay. So, yes, this is commutative. You can use the commutative property of addition to rearrange these. You can solve for one of the functions if you want to, if you need to for any reason. What's the relationship with cotangent and cosecant regarding the graphs that we've seen in the past? Jules? They have the same domain. What about tangent and secant? These have the same domain. What about cosine and sine? Interesting. So the functions that are related in the Pythagorean identities have the same domains as each other. All right, so now for cofunctions. I'm going to write a function. You guys tell me what you think its cofunction is. What is the cofunction of sine of x? Cosine of x. The cofunction of the sine of x is the cosine of x. What about tangent of x? Cotangent of x. And the last one on the list, secant and cosecant. All right, do the cofunctions always have the same domain like they did in our Pythagorean identities? Sine and cosine do. Tangent and cotangent? Nope. Secant and cosecant? So what do the cofunctions have in common? The range. Yep, they sure do. Anything else about the graphs that are similar between functions and cofunctions? Is there a way to make a sine function into a cosine function? A phase shift. Is there a way to make a tangent function into a cotangent function? A phase shift, will that do it? A phase shift and a flip. Okay? What about secant and cosecant? A phase shift and a flip. All right, so while these are not equal to each other, there is a way to make one into the other one. So if I graph a sine function, what would be the equation for the cosine function if I wrote it for that same graph? There is something that we can do a sine function to make a cosine function. We can do the same things to a tangent function to make a cotangent function, and the same things to a secant function to make a cosecant function. The same transformations will take every one of these functions and put it on top of its cofunction. So I want you guys to take a second. I want you to graph sine on your paper. And I want you to write an equation for cosine. Talk about the transformations. Then I want you to see if those same transformations will take a tangent function to its cotangent. You can use your calculator. You can use Desmos.com. But I want you to figure out transformations, the same ones that will take each function to its cofunction. All right, so if we do that, flip it over the y-axis and add a pi over 2, sine and cosine are now equal, tangent and cotangent, and secant and cosecant are now equal. Now you could do that reverse also. You could say cosine of x is equal to the sine of negative x plus pi over 2 also. So this is just some moving and some flipping that makes all of these the same. Pretty cool. All right, now let's look at how we use all this stuff to simplify expressions. We've talked about how in the past we can rewrite a quadratic as its factors. We can rewrite a distribution problem as what we get when we distribute it. We can replace something divided by itself with 1. All of those are identities. So we need to look at all the identities we've written down and see how we can simplify this. Simplifying for most of these problems is going to be taking it from lots of functions, cosine, sine, tangent, cotangent, etc., down to one function, or at least fewer functions. So, does anybody see anything in here that we could use? Anything that you might do? Kate? All right, let's do it. Let's take out the sine of x. Sine of x, what would we call that? GCF, greatest common factor. All right, so example 1 is being written on everybody's paper as we speak. Not telepathically, but physically, we are writing. Example 1. So we get the sine of x times the cosine squared of x minus 1. All right, so we've done one thing, but still I have 2 functions, so I haven't really simplified this too much. What could I do? Okay, to solve it, that's exactly right. We'd set them equal to 0, but this is not an equation, so we're not going to solve it, but hold that thought for later. Shivani, what are you thinking?
We should simplify the cosine part into cosine x plus 1 and cosine x minus 1.
Okay, so if we change this to, I'll just write this down real quick, cosine of x plus 1 and cosine of x minus 1, that is factoring a difference of squares, so that's allowed. But where would we go from there? Saurav?
I was going to move to the first. I was going to suggest a different.
Okay, so Justin, where could I go from here, that blue step? Okay, yeah, we could use the cofunction property and throw some pi's in there with our x's. That could work. Saurav, what was your method also?
I was going to say cosine squared of x minus 1 is equal to negative sine squared of x.
Where's that coming from?
Pythagorean identity.
Okay, so Saurav's suggesting we use a Pythagorean identity. Why would you use a Pythagorean identity? What was your clue that that might be helpful?
I saw cosine squared of x, and generally x all one there, so generally you can use the Pythagorean identity to simplify it into another function.
Okay, so Pythagorean identities are really helpful if you have a function squared. If you don't have a function squared, we can't use them. And Justin's right, I could use a cofunction, but we usually avoid those if we can, because putting pi's in here makes it a little bit more complex. While what Shivani suggested is true, we don't have any identities that will work with that. So we can't get rid of the cosines. So let's try the Pythagorean identity method. Now, Saurav said that we could replace cosine squared of x minus 1 with negative sine squared of x. I'm not so sure that everybody's going to pick up on that instantly. While it is 100% true, Saurav, how do I use this Pythagorean identity and change it into negative sine squared of x?
So you want to get what's in the parentheses to be equal to what's on the left side.
Okay.
So you subtract that 1 there to get the cosine squared of negative 1.
Move this over here to get cosine squared minus 1, okay?
Then you have to subtract the sine squared of x to get that side, you have the left side alone.
Okay. All right. So we can do that. Sort of suggesting we make this equation have this right here in it. So he's suggesting we subtract 1 from both sides and subtract sine squared from both sides. So that will give us cosine squared of x minus 1, because I subtracted 1 from both sides, equals negative sine squared of x, because I subtracted sine squared of x from both sides. So that's one way to do it. There are others. Hannah?
I just don't know where the sine squared came from.
The sine squared?
Yeah.
This one, this sine squared?
Well, just the sine squared in general.
Okay, so that came from this page. Cosine squared of x plus sine squared of x equals 1. That's a Pythagorean identity. So what we're doing is we're taking that Pythagorean identity and we're manipulating it so that we can use it in the problem that we're working with right now. So we wrote down cosine squared of x plus sine squared of x, or I reverse those. That's okay.
But like in the actual equation, I don't see how you made it. So, like, can you just decide it's going to be sine squared?
Can I decide that?
Like, I don't know how you got sine.
Can I decide that this is going to be sine squared?
No, she's saying
Get
how
it from,
we're
like,
not working with
Hold on, one person. Jules, maybe if you want to try it.
Are you talking about the original equation? Like how that relates to it? Are we working with that right now? The original equation? Or...
Okay, so I took the original equation. I factored out sine of x. Do you understand where that came from? Okay, so Hannah's good to this point.
Yes.
All of these are equal, okay? So what we're doing now is we are replacing this with something with a sign in it. Because remember, we're trying to simplify this, and one way I suggested we simplify is trying to get multiple functions. In the original, we had sine and cosine to be just one function. So I'm trying to get rid of either the sines or the cosines so that I have only one function in this problem. Okay? So one way that Saurav suggested, because the only Pythagorean identity, or the only identity I have that has a squared in it, is a Pythagorean identity. If you look through all the other identities we've written down, none of the others have squareds. Okay? And we have a squared right here. So I'm trying to figure out what I have that is equal to cosine squared of x minus 1. And hopefully has a sign in it, because I already have a sign in my function. We're just simplifying. So it takes some getting used to, because you've never done this before. But we're just using the tools that we have to simplify it into something that's a little bit less complicated than what we started with. Okay, so hold on a second, we'll see if we can get you better. Okay, just hold on just a second. I see you're still confused, but hold on just a second, all right? Shivani, did you have something you wanted to add?
is she talking about like the triangle part, like when we were doing like the cosine and then sine, and from the Pythagorean theorem?
Is she asking where this is coming from?
Yeah.
I think, Hannah, you know where this is coming from. Shivani's thinking you're not sure about this. The sine squared of x plus cosine squared of x equals 1.
Oh, I know what that is.
Okay.
It's just the part where you have sine of x and then all of a sudden it's squared. That's the part that we're doing.
We had this right here.
Are we substituting?
Hold on, Kate's gonna try it.
Okay, we're not doing anything with this. That has nothing to do with what we're writing down here. Nothing at all.
That's a substitute.
I'm completely ignoring this right now. I'm only looking at this. That's all I'm looking at. Okay? I didn't change that at all. I'm just trying to find something that I can do differently with this part. Okay? Yeah, the box. The mini boxed. Okay, so what I've just said is that this right here that I just boxed is the same thing as this. I've just used algebra to rearrange it. Does anybody have questions still about how I get from the yellow box to the orange writing right below the yellow box?
Yeah.
We're still confused on that?
Oh, no, I finished.
Okay, who said yeah, we're confused? Nobody said yeah. Okay. So, to figure that out,